Swayam Prabha. Digital India. Educated India.
Hello students, welcome back to this BSc Honours Semester 1 course, which is a core course on Inorganic Chemistry 1. We are discussing about atomic structure, and in first lecture we have discussed various models under atomic structure. In the lecture 2 we will be continuing with the further topics. This is Professor Ravin Zugade from Department of Chemistry, Rashtrasanta Tukadoji Maharaj Nagpur University, and the lecture has been prepared under the expertise of Professor L.J. Paliwal from the same department. Outline of this particular lecture: it involves topics like de Broglie concept of matter waves, Heisenberg uncertainty principle, Schrödinger wave equation, properties of the wave function, quantum numbers, and in the end we will be discussing about Pauli's exclusion principle. So let us start with de Broglie concept of matter. This concept is actually the concept or hypothesis which assumes the dual nature of matter. According to quantum mechanics, we know that the electromagnetic radiation is associated with quanta of radiation. So the quantum mechanics suggests that the transition of energy does not take place in a continuous manner, but it takes place in the discrete manner in the form of packets of energy or quanta of energy. Now, de Broglie hypothesized exactly opposite of this. What he suggested, that as the electromagnetic radiation has packets associated with it, the material particles in motion like electron, they are associated with wave. So as waves are associated with packets or quanta, similarly the material particles which are in motion, they are associated with a wave. It was a hypothesis by de Broglie in 1924. Now it means that each particle has a dual nature, particle nature as well as wave nature, and this wave is called as de Broglie matter wave. It is different from the electromagnetic wave, but what we call it as a matter wave. It means that the particle and wave, both of them exist simultaneously and they are associated with each other for the microscopic particles. Now when I say that it is having particle nature, it means that it will have properties of particle. What are the properties of particle? Mass, volume. These are the properties of the particle. And when you have a wave nature of the matter, it means that it will have wave properties like wavelength, frequency, velocity, and so on. Now, if the particle is there with mass m, then it will have an energy given by E is equal to m into c square, where m is the mass of the particle and c is the velocity of light. So if you have a particle having mass m, then its rest mass energy is given by E is equal to m into c square. This is a well-known Einstein's equation. Now if you have a wave associated with it, it will have some wavelength, and energy of this wave is given by E is equal to hc upon lambda. So now the energy depends on lambda. Here the energy depends on mass. So this is corresponding to the particle nature, this is corresponding to the wave nature. Now according to the concept of de Broglie, we will combine these two equations and what we get is m into c square should be equal to hc upon lambda if both the particle and wave correspond to the same material. It means that lambda will be equal to h upon m into c. Now where c is the velocity of light. Now if the particle is already in motion, then this value of c can be replaced with the particle velocity v. So let us replace this with v, and what we get is lambda is equal to h upon m into v, or lambda is equal to h upon p, where p is the momentum. Momentum is defined as the product of mass and velocity of a particle. So if we observe this equation carefully, lambda is equal to h upon p, we will find that this lambda is a property of a wave. It means that it represents the wave nature of the matter, whereas momentum is a property of a particle because momentum is associated with mass. Hence, we can say that this equation is a combination of wave nature on left side whereas particle nature on right hand side. So it's a combination of both of them. This is de Broglie equation of matter wave. On one side there is a wave nature, on other side there is a particle nature. Now the concept of de Broglie was put forward in 1924. After 3 years of this, Davison and Germer, they carried out an experiment to prove the de Broglie concept. So this is actually Davison-Germer's experiment which could be used as a verification of de Broglie concept. What Davison and Germer did, they carried out an experiment in 2 steps. In the first step, what they did, they took a coil, applied potential to a heated coil so that it will generate electron beam, and this electron beam was accelerated by applying potential to the anode, and this beam was focused and was made to incident on a nickel crystal which is used as a target, and a movable detector which was moving in a circular manner recorded the intensity of the diffracted beam of electrons. Actually, this experiment in the first part considers electron as a wave. Now, if electron is a wave, then it will undergo diffraction by some angle theta and it will be detected by the movable detector at different angles. So the intensity of the wave is detected at different angles. In the first step, what Davison and Germer did, they kept this applied potential constant and they recorded the theta value. So they changed or varied the value of angle of this detector. At different angles, different intensities were obtained, and it was observed that the first maximum intensity was obtained at an angle of 50 degree. So at 50 degree angle, we are getting maximum intensity. That is the first observation. Now they kept this 50 degree as constant angle. So they fixed the position of this movable detector. And in the second part of this experiment, they varied the applied potential. When they went on changing the applied potential, the intensity which is recorded by this detector goes on changing. With increase in applied potential, initially it was observed that the intensity goes on increasing, increases up to a particular value, and then it goes on decreasing. And the maximum intensity was obtained at an applied potential of 54 volts. So these are the two important values which were obtained from Davison-Germer experiment. Maximum intensity of the wave at 50 degrees and maximum intensity of the particle at 54 volts applied potential, because the particle will get accelerated when you go on applying the potential. Acceleration cannot be for the wave. Acceleration can be there only for the particle. So first part of the experiment, considering it as a wave. Second component of the experiment, considering it as a particle. Out of these two observations, what Davison and Germer they found, if we consider the electron as a wave, then we can apply Bragg's equation to this particular experiment. According to Bragg's equation, 2d sine theta is equal to n lambda, where d is the interplanar distance in the nickel target, theta is the angle of diffraction, n is the order of diffraction, and lambda is the wavelength of the radiation. Now, the theta value obtained from the Davison-Germer's experiment was found to be 50 degree. So theta is 50 degrees. Then for the nickel crystal, the interplanar spacing is 0.91 angstrom, and for first order diffraction, n will be equal to 1. So if we put the value of theta, d and n in this equation, what we get is lambda equal to 1.65 angstrom. This is what we call as the wavelength of the wave which is associated with the electron beam. So it is found to be 1.65 angstrom. Now, for the second part of the experiment, if the momentum of the electron, when you apply EMF V volts, the momentum is given by under root of 2eVm, where E is the charge on electron and V is the applied potential, m is the mass of electron. Now E is constant, m is constant, so it means that the momentum of the electron will be completely governed by the applied potential V. Now here the applied potential was found to be maximum. For maximum intensity it was 54 volts. Putting the value of 54 volts, we get the value of P, and putting the value of P in the de Broglie equation, that lambda is equal to h upon P, we get the value of lambda as 1.66 angstrom. So if we compare these two values of 1.65 and 1.66, they are approximately equal. So from both the experiments or both the components, we are arriving at the same value of lambda. It clearly indicates that the material or the electron is associated with a wave. Conclusion is, electron behaves as a wave as well as a particle. Particle with a momentum and a wave with a wavelength. Now what is the significance of this de Broglie equation? The de Broglie equation is given by lambda is equal to h upon m into v or h upon p. Now this equation shows that the wavelength of the material particle is inversely proportional to linear momentum. So when p goes on increasing, lambda goes on decreasing. H is Planck's constant, so that is going to be constant. So now there is a relation or inverse proportion between lambda and p. Secondly, for big or macroscopic particles, the mass is very large, and since mass is large, the value of p becomes very high. And if p increases, the lambda becomes too small to be measured, or we can say that for macroscopic particles, the value of wavelength is insignificant, or we can say in other words, the wave associated with a macroscopic particle is insignificant. Thirdly, larger particles do not show wave-particle duality because the wavelength is extremely small or negligible. And the microscopic particles like electron, they have negligible mass, and so the wavelength becomes significant for tiny minute particles with very small mass and very high velocity. Now, we will see the de Broglie explanation of quantization of angular momentum. Now, according to Bohr's theory, the angular momentum of an electron is quantized. It means that electron cannot have any value of angular momentum, and the value of angular momentum are integral multiples of h upon 2 pi. It means that the values of angular momentum are nh upon 2 pi, where n is an integer. This is the concept or Bohr's theory we have discussed in the previous lecture. Now, we will try to find out why this happens, that the angular momentum is also quantized. The de Broglie explanation on the basis of wave-particle duality gives a clear insight into this particular aspect of quantization of angular momentum. If you have a Bohr's orbit having a radius r, then if an electron is moving in this particular orbit as postulated by Niels Bohr, what we call it as a stationary state or the Bohr orbit, an electron is revolving here. Now, if there is a wave associated with the electron, what will happen? In order to have a constructive interference of the wave, it is necessary that the wavelength and this circumference of this orbit should be proportional to each other, or they should be multiple of each other. In other words, the orbit perimeter should be an integral multiple of the wavelength. Otherwise, what will happen? The wave will cause a destructive interference and it will be completely destroyed. Hence, we can say that the circumference of this particular orbit is 2 pi r, or perimeter is 2 pi r, that is equal to n times the wavelength, or integral multiple of the wavelength. So we will rearrange this. This is equal to lambda. Now we know that lambda is equal to h upon p according to de Broglie equation. So 2 pi r will be nh upon p, or nh upon m into v, where m is the mass of the electron and v is the velocity of the electron. Now this velocity is a linear velocity. Now we rearrange this equation as m into v into r will be equal to nh upon 2 pi. Now this m into v into r is the angular momentum of the electron. If we consider m into v, we call it as a linear momentum, and mv into r is the angular momentum. And this angular momentum is now equal to nh upon 2 pi, or what is postulated by Bohr's theory, it is the integral multiple of h upon 2 pi. Now h is constant, pi is constant. It means that the angular momentum depends on the value of n, and n what we call as the principal quantum number. So for different values of n, we will have discrete values of angular momentum, and those are the only allowed values of angular momentum where this equation will be fulfilled. So electron can be present only in those orbits in which this particular equation is fulfilled, and the angular momentum becomes integral multiple of h upon 2 pi. So this is clearly proved by de Broglie concept what Bohr's theory has postulated. Now let us compare the wavelength associated with an electron moving with a velocity of say 10 raised to power 6 meter per second and a cricket ball which is weighing about 100 gram and moving with a speed of 150 kilometer per hour. And we will comment on what is the observation, what our observation we get. So for an electron, the mass is 9.1 into 10 raised to power minus 31 kg. And Planck's constant here is 6.626 into 10 raised to power minus 34 joule second. Now we will apply the de Broglie concept. So for an electron, we know that according to de Broglie equation, lambda is equal to h upon p or h upon m into v. So that is equal to 6.626 into 10 raised to power minus 34 divided by 9.1 into 10 raised to power minus 31, which is mass of electron, and v is the velocity of electron given as 10 raised to power 6 meter per second given over here. So now the value of lambda is coming out to be 7.27 into 10 raised to power minus 10 meter, which is 7.27 angstrom we can say. So it's a measurable value of wavelength associated with an electron. Now if we try to apply the same logic to a macroscopic particle or a body like a cricket ball weighing 100 gram, which is 0.1 kg, moving with a velocity of 150 km per hour, converting this into meter per second, we get 41.66 meter per second. Now if we put this value of mass and this value of velocity in the de Broglie equation, what we get is lambda is equal to h upon m into v, which is 6.626 into 10 raised to power minus 34 divided by 0.1 kg into 41.66 meter per second, and what ultimately we are landing up with is the value of lambda as 1.59 into 10 raised to power minus 34 meter. Now if we compare these two values, we will find that 7 into 10 raised to power minus 10 meters for electron and 1.59 into 10 raised to power minus 34 meters for the macroscopic body like a cricket ball. It means that this value is totally insignificant. So we can say that wavelength of the ball is too small to be measured, and so for macroscopic particles de Broglie concept has no physical significance. This is the inference we can get, and why we can apply this de Broglie concept to only microscopic particles like electron. This is all about the de Broglie concept. Now we come to another important concept, that is the Heisenberg's uncertainty principle. What this principle states? This states that it is not possible to measure simultaneously both the position and momentum of a small moving particle with absolute accuracy or certainty. In other words, we can put it in other form. Mathematically, the Heisenberg uncertainty principle can be stated as the product of uncertainty in position and momentum is always constant. Mathematically, this can be put as delta x into delta p is greater than or equal to h upon 4 pi, where delta x is the uncertainty in position of the particle and delta p is the uncertainty in the momentum of the particle. H is the Planck's constant. Now if we see the right hand side of this equation, we will find that h upon 4 pi is constant. It means that the product of these two should be or will be always greater than some constant value. In other words, if we try to decrease delta x, delta p will go on increasing, or vice versa, if we try to decrease the value of delta p, the delta x value will go on increasing, so that the product is always greater than or equal to h upon 4 pi. In other words, we can say that if we try to locate the electron or locate the particle extremely precisely, there will be large error in momentum, or if we try to determine the momentum with extreme precision, then there will be a large error in the or large uncertainty in the position. This is called as Heisenberg's uncertainty principle. Now, what is the physical significance of Heisenberg's uncertainty principle? Let us try to explain this in terms of the motion of the electron. Suppose an electron is moving in a particular orbital and we want to observe this electron to determine its position and its momentum simultaneously and accurately. Now, in order to observe the electron, what is the requirement? The requirement is that the electron should be visible. So, in order to see the electron, we should have a high resolution microscope. And second condition is that there should be incident radiation which should get reflected and enter into the microscope. So, the incident photon should incident on the electron and should enter into the microscope in order to see the electron clearly. But since the mass of the electron is very small, when the photon incidents on it, it changes the velocity as well as the path of the electron. In other words, if we want to see accurately the electron, what will happen? The velocity will get altered. And if we try to measure the velocity accurately, or the momentum in other words accurately, then we will make a large error in the position. Hence, it is not possible to determine two things simultaneously and accurately with high precision: the position and the momentum. Consider an example. A microscope using suitable photon is employed for locating an electron in an atom within a distance of 0.1 angstrom. So when I say within a distance of 0.1 angstrom, it means that this is the uncertainty in the position. Calculate the uncertainty involved in the velocity. Given the mass of the electron is this much and a Planck's constant is 6.626 into 10 raised to power minus 34 joule second. Now we'll try to solve this. So what is given is uncertainty in the position allowed is 0.1 angstrom, that is 0.1 into 10 raised to power minus 10 meter. H is the Planck's constant and m is the mass of the electron. Now according to Heisenberg uncertainty principle, we can say that delta x into delta p is always greater than or equal to h upon 4 pi. So this value will be minimum when delta x into delta p will be equal to h upon 4 pi. So putting this as equality, what we get is this delta x is 0.1 into 10 raised to power minus 10. Delta p is to be calculated. H upon 4 pi we can calculate, and the value of delta p comes out to be 5.27 into 10 raised to power minus 24 kilogram meter per second. Now even if we see this appears to be a very small value of delta p. But now this delta p is a combination of two parameters. The first one is the mass and second is the velocity. So if we try to calculate this delta v value, so it will be delta p upon mass of electron, and the value of delta v comes out to be 0.579 into 10 raised to power 7 meters per second. Now if you see this value, this is a very large value of delta v. Now delta represents the uncertainty in the velocity. So the uncertainty in velocity is of the order of 10 raised to 6 to 10 raised to 7 meters per second. So if you try to reduce the uncertainty in the position to 0.1 angstrom, we are making a large error in the value of velocity, or uncertainty in the velocity is very high. So that is very large uncertainty in the velocity. That is why it is not possible to do or to determine the two things simultaneously and accurately. If we try to decrease this, the value of delta x will go on increasing. Now the same analogy we will apply to the cricket ball, a macroscopic body weighing 100 gram, and it is to be located within 0.1 angstrom, the same uncertainty in the position. Now let us see what is the uncertainty in the velocity. Again, according to our equation, you have delta x into delta p is greater than or equal to h upon 4 pi. So, in terms of velocity, it will be delta x into m into delta v is equal to minimum value is h upon 4 pi. So, putting the values of delta x is equal to 0.1 into 10 raised to power minus 10 meter, mass is 0.1 kg, that is 100 grams, delta v is to be calculated, and h upon 4 pi, the constant values. If we put these values, what we get is delta v equal to 0.4527 into 10 raised to power minus 22 meter per second. Now we can observe that this is a negligible uncertainty in the velocity. For the same uncertainty in the position, we have negligible uncertainty in the velocity because the particle has got large mass. The mass of electron is negligible, so the uncertainty in the velocity is high. Here the mass of the particle or mass of the ball is high or large, and so the uncertainty in the velocity is negligible. Hence, we cannot apply the Heisenberg's uncertainty principle to the macroscopic bodies like cricket ball. So this is all about the Heisenberg uncertainty principle. Now we come to the third topic of this lecture, that is the Schrödinger wave equation. Now, Erwin Schrödinger, he was an Australian physicist, and he proposed that if electron is behaving as a wave as postulated by de Broglie, then it should have a wave equation. Now, every wave has got its own equation, and if there is a material particle like an electron and a wave associated with it, such particle wave will also have an equation associated with it. And he derived the equation of a wave propagating in the 3 dimensions along with the particle, and such equation was known as Schrödinger wave equation. According to this Schrödinger wave equation, you have del 2 psi by del x square plus del 2 psi by del y square plus del 2 psi by del z square plus 8 pi square m upon h square e minus v into psi is equal to 0. Or if we take this psi common out of this bracket, then del square by del x square plus del square by del y square plus del square by del z square into psi will be equal to plus 8 pi square m upon h square e minus v psi will be equal to 0. Or this particular operator is shown by this del square psi plus the same value is equal to 0. So you can put it in all the 3 forms. This is called as Schrödinger wave equation. And in this equation, the V is the potential energy of the system, E is the total energy of the system, M is the mass of the particle, H is Planck's constant, and psi is called as the wave function. Now, if you see this equation carefully, it contains the properties of the particle like mass and E minus V. E is the total energy and V is the potential energy. So difference between these two will be the kinetic energy. So E minus V is the kinetic energy of the particle. So it is related to mass and kinetic energy of the particle, which is actually having a wave associated with it with a wave function psi. This is Schrodinger wave equation in 3 dimension. If we want to put it in 1 dimensional space, then it will be only del square psi by del x square plus 8 pi square m upon h square e minus v into psi will be equal to 0 along x direction. Now what is the significance of this psi and psi square? We will try to understand. Now according to Schrodinger wave equation, you have psi is a function of x, y and z coordinates. So it is in the space. The value of psi is actually what we call as a wave function of the wave which is associated with the matter or particle. The wave function psi can be positive, it can be negative, it can be real or it can be imaginary also. What it represents? So psi represents the amplitude of the electron wave. Now we know that amplitude is the property of a wave, and electron or the particle is moving and along with it there is a wave. So wave will have a particular amplitude at each location. So that amplitude is given by psi. Now we know that square of amplitude represents the intensity. Similarly, square of the wave function, that is psi square, it represents the probability of finding the particle in a particular region. However, this wave function psi is said to be a well-behaved wave function if it fulfills 4 important conditions. The first condition is psi should be continuous in nature. It means that the value of the amplitude of the wave or wave height should continuously go on changing in a periodic manner, or it should be a continuous function. It should not have any discontinuity involved in it. Secondly, psi should not be infinite at any point. It should be finite and it should vanish to 0 at infinite distance. So it should be limited in a particular region. Thirdly, this psi should have a single value at any point. So if we consider at any point in the space with some coordinates x, y, z, then for those values of x, y and z, psi should not have 2 values or more than 1 values. It should have only single value at that particular point. And fourth and probably most important condition is the integration of psi square over entire space should be equal to 1. It means that integration of psi square, now we know that psi square represents the probability. So the overall probability over the entire space, that is the total probability in the space, should be equal to 1. That is, integration of psi square should be equal to 1. So if a particle exists, it should exist in the entire space with single probability, or the total probability should be equal to 1. This is a diagrammatic representation of psi and psi square. So these are the probabilities, or these are the distributions of values of psi. Psi can have the values like this. Psi can have positive or negative value. Psi can have real or imaginary values. But the value of psi square will always be positive and real values. And that's why normally what we say is psi has no physical significance as such, but psi square has got an important significance, that it represents the probability of finding a particle in a particular distance. And as it can be seen that if we integrate the value of this psi square over the entire space, it should come out to be equal to 1. For positive values of psi, negative values of psi, or even for imaginary values of psi, all the psi square values are positive as well as real. Now what is meant by a normalized wave function? See, we have seen that the probability of finding a particle like electron in a small volume element, suppose d tau is a small volume which is a product of dx into dy into dz, then the probability of finding the particle in this particular volume is given by psi square into d tau, or if the value of psi is complex number, then for such a number, square instead of psi square we take psi into psi star. This psi star or psi asterisk is actually the complex conjugate of psi. So if the value of psi is of the form a plus ib, then psi asterisk will be a minus ib, or if psi is a minus ib, then psi asterisk will be a plus ib, so that the product should be positive real number. Then the total probability of finding the particle in the entire space is given by integrating this value, that is psi square into d tau, between the limits minus infinity to plus infinity. So if we integrate it over the entire space, then in order to be a well-behaved wave function, for a well-behaved wave function, this integration should come out to be equal to 1, so that the total probability of finding the particle in the entire universe or in the entire space is equal to unity or is equal to 1. Such condition, if it is fulfilled, then the value of psi or the wave function psi is called as normalized wave function. Now in some cases, for certain functions, it is not possible to get such value of psi into psi star d tau is equal to 1. But in some cases we find that this integration comes out to be some constant value n. Then in that case it can be normalized by using a normalization condition. We will see how to normalize this wave function. So if psi into psi star d tau, its integration, if it is equal to some constant n, then we can take this n value on left hand side and we can normalize the wave function as a product of 1 by root n into psi into 1 by root n into psi star d tau is now equal to 1. So in this case, we can say that now the new wave function, which is 1 by n into psi, is a normalized wave function. And this particular procedure what we have followed is called as normalization of the wave function. So either the wave function should be normalized or it can be normalized by applying this normalization condition. Another aspect is if you have a wave equation with two different solutions having values psi m and psi n, then these psi m and psi n, they are said to be orthogonal wave functions if their product comes out to be 0 over the entire space from minus infinity to plus infinity. Or mathematically, if we try to place it as integration from minus infinity psi m psi n star d tau is equal to 0, and similarly psi m star into psi n into d tau is again equal to 0. So such wave functions which fulfill such conditions, they are said to be orthogonal wave functions. They are orthogonal to each other. Now if psi m as well as psi n, they are normalized and also they are orthogonal to each other, then they are said to be orthonormal wave functions. So they are orthogonal as well as normalized, normalized within themselves and orthogonal to each other. Normalization is a property or inherent property of one particular wave function, whereas orthogonality is a property of product of two different wave functions or two different solutions of a wave function. Now we come to an important aspect of what is called as quantum numbers. Now, quantum numbers is actually a set of 4 integers which are necessary to locate the energy level or position of an electron and to specify the size, shape and orientation of the orbital, and such set of numbers are called as quantum numbers. There are 4 quantum numbers, namely principal quantum number, azimuthal quantum number, magnetic quantum number and spin quantum number, denoted by symbols N, L, M and S respectively. We are going to discuss all the 4 quantum numbers in details. In short or in brief, we can say that these are the 4 numbers which are important or which are necessary to determine the position of the electron, also specify the shape, size and orientation of the orbital in which the electron is moving. The first quantum number among the 4 is the principal quantum number. It is not principal, but it is principal. That is the main quantum number, we can say. What this principal quantum number signifies? It signifies the main energy level or main shell of an electron. So it represents the main shell of an electron, denoted by symbol N. Secondly, this principal quantum number has positive values like 1, 2, 3, 4, etc. Every value of this N, like 1, 2, 3, etc., corresponds to a shell, and these shells are denoted by symbols K, L, M, N, etc. That is, when I say that N equal to 1, it means that it is K shell, N equal to 2, L shell, and so on. So every value of N corresponds to a particular shell in the atom or the main energy level in the atom. Fourthly, we can calculate the maximum number of electrons present in any shell by using equation 2 into n square. For example, for K shell, the value of N is 1. So 2n square comes out to be 2. It means that K shell has a capacity of 2 electrons. Similarly, L shell has a value of N equal to 2. So 2n square will be 8. So L shell has a capacity of 8 electrons. Similarly, M shell with a capacity of 18 and N shell with capacity of 32 electrons. So this value of N can be used to calculate the maximum number of electrons present in the main energy level or the main shell. Next is, as the value of N goes on increasing, the radius of the shell also goes on increasing. The Bohr's radius is related to the principal quantum number by a formula Rn, or that is the radius of the nth Bohr's shell or Bohr's orbit, is equal to n square h square upon 4 pi square z m e raised to power 2. Now if we see this carefully, we will find that the value of n will govern the value of Rn. That is, as the value of n goes on increasing, the radius goes on increasing. Energy of nth Bohr's shell or energy of an electron which is revolving in the nth Bohr's shell is given by minus 2 pi square m e raised to 4 upon n square h square. Again, this value of n is playing an important role in deciding energy of a particular Bohr shell. Or if we put all these constants, the value of En comes out to be minus 1312 upon n square kilojoule per mole. It means that this energy of an electron revolving in the nth shell is a function of only the principal quantum number. Second quantum number is the azimuthal quantum number. Now this has got different type of physical significance. Azimuthal quantum number represents subshell of an electron. As the principal quantum number represents shell, the azimuthal quantum number represents subshell of an electron, and azimuthal quantum number is denoted by symbol small l. Now every value of L corresponds to a subshell, like L is equal to 0 corresponds to subshell S. L is equal to 1 corresponds to subshell P. L equal to 2 corresponds to subshell D, and L equal to 3 corresponds to subshell F, and so on. Now these symbols S, P, D, F, they have been obtained or derived from the characteristic spectral lines obtained from these subshells. This S stands for sharp, P stands for principal, D stands for diffused, and F stands for fundamental. Also, we can use the value of L to calculate angular momentum of an electron, which is given by under root of L into L plus 1 h upon 2 pi. Now, if we see this h upon 2 pi is constant, it means that the angular momentum of an electron in any subshell is only the function of value of L. One more significance of the value of L is that since every subshell has different shape, one can determine the shape of the subshell depending on the azimuthal quantum number. For example, S subshell has azimuthal quantum number 0 and the shape of this subshell is spherical. Similarly, azimuthal quantum number 1 corresponds to P subshell with a dumbbell shape. Azimuthal quantum number 2 corresponds to D subshell with double dumbbell shape. Azimuthal quantum number 3 corresponds to F subshell with a complex shape. Also, it is possible to calculate the maximum number of electrons in a subshell by using the value of L, and the maximum number of electrons in a subshell is given by 2 into 2L plus 1, as the value of number of electrons in a shell or main shell is given by 2n square. Similarly, maximum number of electrons in a subshell is given by 2 into 2L plus 1. For example, for subshell S, the value of L is 0, so maximum number of electrons will be 2. For P, maximum number of electrons will be 6. For D subshell, the maximum capacity is 10. For F subshell, the maximum capacity is 14. So the value of L can be used to calculate maximum number of electrons present in a subshell. Also, if you have any value of N, then this L will have N number of values. That is, for every value of N, there are N values of L. For example, if N equal to 1, then L will have only one value, that is 0. So we can say that in K shell, N equal to 1 and it has got only one subshell S. For N equal to 2, L has got two values 0 and 1 corresponding to two subshells. It means that in L shell, there are two subshells S and P. Similarly, there are three subshells in M and four subshells in N shell. Third quantum number is the magnetic quantum number. What it signifies, it describes the behavior of an electron in the presence of external magnetic field. Now, if we place an atom in an external magnetic field, the angular momentum vector, it acquires 2L plus 1 orientations, and hence for every value of L, there are 2L plus 1 values of M, and this M is the magnetic quantum number, and it will have values from minus L to plus L through 0. Hence, the magnetic quantum number M can have different values. For example, in S subshell, L has value 0. So M will have 2L plus 1, that is only one value, which is equal to 0, which corresponds to an orbital S. Similarly, for P subshell, the value of L is 1. So 2L plus 1 becomes 3. So M will have three values from plus 1 to minus 1 through 0. That is minus 1, 0 and plus 1. These three values correspond to three orbitals Px, Py and Pz. Similarly, in case of D subshell, there are 5 values of M corresponding to 5 d orbitals. In case of F subshell, there are 7 values of M corresponding to 7 orbitals due to 7 values of M. And the fourth quantum number is the spin quantum number. Now we know that when an electron is revolving around the nucleus, at the same time it is spinning around its own axis, and this is called as spin motion of an electron. And such spinning electron, it behaves as a tiny bar magnet. Now this spinning motion can be of two types. It can be clockwise motion or it can be an anti-clockwise motion. So electron can move in a clockwise manner or it can move in an anti-clockwise manner around its own axis, while it is simultaneously moving around the nucleus in a particular shell and subshell. Now corresponding to these two motions, there are two quantum numbers, plus half and minus half, that is plus 1 by 2 and minus 1 by 2. The directions are opposite, values are equal. One is clockwise, second is anti-clockwise. Hence, this corresponds to, or this is represented by a symbol S, that is spin quantum number represented by S, having values either plus 1 by 2 or minus 1 by 2. This can be shown as two different motions, and we know that every orbital has a capacity of 2 electrons, and these 2 electrons will have always opposite spins. So if one electron is moving in a clockwise direction, the other has to move in an anti-clockwise direction. So these are represented by upward arrow and downward arrow, or the spin quantum numbers plus half and minus half. The value of half is because there should be a difference of 1 according to the principle of quantum numbers, and they should have exactly opposite values. So plus half and minus half are the only two values which are differing by 1 and having opposite signs, and so the values allotted or assigned to the spin quantum numbers are plus 1 by 2 and minus 1 by 2. So let us summarize the quantum numbers. So the principal quantum number, it represents the main shell of an electron, and these shells can be K, L, M, N. For example, if we consider this particular electron which is moving, it is moving in the K shell, so it will be having the principal quantum number of 1. Similarly, the azimuthal quantum number represents subshell of an electron. Like if an electron is moving in a S subshell or P subshell or D subshell, then the azimuthal quantum number will be accordingly L is equal to 0, 1, 2, etc. Third quantum number is the magnetic quantum number, which represents the orbital of an electron. For example, if an electron is moving in a p orbital, then it can have, or p subshell, it can have px orbital, py orbital, or pz orbital. The spin quantum number represents the direction of spinning of electron, that is clockwise direction plus 1 by 2, and minus 1 by 2 represents the anti-clockwise direction of rotation of an electron. And in a particular orbital, there are only 2 electrons with opposite spins. Then only they will remain in a particular orbital. Parallel spin electrons cannot remain in a single orbital. That is what we call as the spins paired in a orbital. This is all about this particular lecture. We will continue the remaining part of this atomic structure topic in the lecture number 3. Thank you very much.